Count down. Okay. On that assignment that I just gave back, that is like the first of many left games beginning. Some of you are still struggling with addition and subtraction versus multiplication and division. So let's say that you've got 356.17, and you're going to add that to 5.8, okay? Their distances, volumes, whatever they are, okay? So if I'm adding these, true or false, this only has 2 significant digits, therefore my answer can only have 2 significant digits.
False.
False. What do you worry about? Precision. What's the least precise measurement?
5.8.
This. Go to this. So on the test tomorrow, and you're going to have a problem like this, trust me, okay? If you don't know what to do, line them up, stack them, align the decimal points. Find the least precise measurement, add it together, and round to that value, okay? Punch it in your calculator. You're going to get 7, 9, 11, 6, 361.97, okay? This is the least precise measurement rounded to that. So how are you going to write this answer? It's actually a little bit tricky.
362.0.
Yeah, you got to write it as 362.0, okay? Because you got to round it all the way up. But then you've got to put the 0 on the end of it to indicate, hey, that's the precision that we have, okay? So don't forget this. Now, if I were multiplying these two numbers together, then how many significant digits could I have?
2.
2. Okay, so somebody out of curiosity, take your calculator, tell me, take 356.17 times 5.8.
2065.
2065.
0.786.
0.786, okay? Your calculator says this is the answer. You can only have 2 significant digits. So how are you going to write that answer with 2 significant digits? There's a couple ways you can do it. What's one of them?
2,100.
Yeah. I could just write 2,100, okay? And you're all going, oh, but that just seems so weird to only write it as 2,100. Look, this is only has 2 significant digits. Because if you write this, it looks like you had great data. You don't, okay? If you've got just okay data, you can only have a just okay answer, okay? That's it. Now, how else could I write that with 2 significant digits?
2.1 times
2.1 times
10 to the third.
third, okay? That's it. Now, what if these zeros were actually significant? What if I actually needed 4 significant digits? Then what could I do?
2.100.
I could put 2.100 times 10 to the third. That's an option because everything in scientific notation is significant. What else could I do?
Add a decimal point.
I can put a decimal point out here, okay? Because if there's a decimal point, which direction do you count?
Right.
Decimal point, you count right. You find the first non-zero digit and you count everything to right. So this would have 1, 2, 3, 4. There's another option.
Put a line over it.
Yeah, go old school and go, oh, these are the chosen freshmen. They're with me. They're cool. Okay? Either one of those. Now, but what if you put 2100.0? Then it has 5. Okay? So I promise you tomorrow, you're going to have to work a multiplication and division problem like this, and you're going to have to work an addition and subtraction. It's going to be on the back side of the test. That's where it's going to be. Okay? Nick?
So for like number 5, we're adding 2, so you have to like add the kilograms and then grams together, so you have to convert the grams.
Yes, but you're still going to pick the least precise measurement to determine how that's going to be written.
Okay, so you'd have to first convert and then determine the least
Yeah,
precise.
because that's the only way you can compare them. Otherwise, you're comparing apples to oranges.
Okay.
Okay? Yeah, you can't do that unless they're in the same units. Okay. Anything anybody want me to go over on that assignment that I gave you yesterday that's going to be due tomorrow?
Oh,
On 7, do you want us to substitute in, like, so it's called the following equation for acceleration?
Oh, yeah, I thought number 7, let's talk about 7C, okay, because that's one of the more difficult ones. So, let's just make sure everybody's on the same page. So I've got distance equals 1/2 AT squared plus V naught time. So let me explain how I could use this equation on the test tomorrow. And this is one of your go-to equations that you will use in all of physics. Okay? So this is your distance. Here's your acceleration, second squared V naught time. So what I might do is I'll say, hey, just prove that this equation is valid using dimensional analysis. I promise you, you're going to have to do dimensional analysis tomorrow. I promise you, if you hand in your test and you haven't done it, whoa, don't hand in the test. Okay? So, we're going to do dimensional analysis. What's the first step?
Put everything in units.
Yeah, put in the units. Are you going to worry about the 1/2 when you do dimensional analysis? Mary, why not?
Because you don't want to actually have any values for the 1/2 to apply to.
Yeah, and it's not going to change any of the units. Okay? So, Olivia, what are the units for acceleration?
Meters per second squared.
Beautiful. Okay? Now, Vonda, when I square seconds, what's going to happen?
15 seconds squared.
Yeah. Right? So then, Michael, V naught, what's that going to be measured in? So velocity, what's velocity measured in?
I don't remember.
Let me give you a hint. It ends in per second.
Per second. Meters per second.
Beautiful. There you go. Meters per second. And then time's going to be in seconds. Okay. So at this point, you're going to show, oh, the seconds cancel out, the second squared cancels out. I end up with meters per plus meters. Now, when I do this, do I end up with 2 meters then? No. What do I end up with?
meters.
Just meters, because all I'm showing is that I can add meters to meters. Okay? So this becomes meters. That equals meters over there. Is the equation valid?
Yeah.
Yeah. And that's one of the things that if you do this long enough, it just becomes second nature. That the more you do this, you look at it and just go, oh yeah, those cancel out, I get meters plus meters, hey, we're golden. Okay. Now, this is how I would tackle this problem if you asked me to solve it for acceleration. Keep in mind, I loathe fractions. They're necessary evil, but I really don't like them. I want to get rid of them if I can. So what can I do to get rid of that 1/2?
Multiply by 2.
More, just one side?
No, both sides.
Both sides, right? Because we want to maintain equality, right? We want to maintain equality. So I want to multiply both sides of this equation by 2. So we get 2x equals AT squared plus 2V naught time, right? Go with this. Now, you don't have to do it this way. This is just how I would do it, okay?
Mr. Rickman,
Yes?
I think it's just a V naught T, not 2 V naught T.
No, but I multiply everything by 2
Okay.
to get rid of the fraction.
I see what you're
Yeah, okay? We're good?
Yeah.
Okay. Now what am I going to do?
Subtract the 2 not 2.
So I'm going to have 2x minus 2v naught t, 2v naught t, then what? Divide by
T squared.
t squared equals a. Boom, there you go, you're off to the races. Now, again, if you did this right, what unit should you get? Meters per second squared. Okay, I got second squared down here. Okay, that's cool. This is just meters. Okay, I'm cool there. When I take meters per second times seconds, I get meters. So I get meters on top divided by second squared. That's acceleration. Hey, we're off to the races. Okay?
So are we supposed to do the dimensional?
No. No. This is all you have to do. Not do the dimensional analysis. Do not do the
No,
dimensional
that's all I was
analysis.
asking, I was like,
No. But if you do this long enough, you just look at it and go, okay, hey, I did it right. So when you get done with it, if you want to do that, You can't, because if I don't get meters per second squared out of this, it doesn't work. Okay? Nick?
On the review, like when you would have a, like for example, 5b or 5a even,
Yeah.
like the answer would be like square rooted. So would you have to put the plus and minus in front of it, or
Technically, yes, but I'm not gonna worry about it.
okay?
Now, let's talk about number 6 though, okay? Because I want to, hopefully you all didn't do this, but I'm guessing some of you did. Okay? This is one of the absolute go-to equations in this class. It's actually over the years become known as that equation, okay? Literally. So when we get, this is really the next unit when we deal with velocity and acceleration. And if I say that equation, this is the one I'm talking about. This is that equation. So you want to get V naught by itself. So what are you going to do? Subtract 2ax, right? Equals V naught. Everybody cool with that?
V naught squared.
Yep. And that's squared, so then I'm going to do what?
Square root.
Square root both sides, okay? Now here's the $1 million question, okay? Here's the $1 million question. Can I write this as V minus, that's minus, the square root of 2ax equals V naught?
No.
No, do not do this, okay? This is bad. Do not do this. Because this is being subtracted. You cannot just take the square root of that by itself and leave everything else, okay? This whole thing has to stay together. So do not do this. This is as far as you can go on number 5. Do not write the square root of, or V minus 2a, the square root of 2x. It will not work, okay? Don't do it. Don't do it. Okay. On the back side of the question with the pendulum, okay, let me give you some hints. On that one, on number 8b, where you're finding the length of the pendulum, that length should be between 0.5 and 1 meter. A little closer to 0.5. Okay? On 8d, where you're finding the gravitational acceleration on planet Zoltar, that should be between 3 and 4 meters per second squared. Now, little historical perspective. Apollo 11 mission landed on the moon. Who's the first man on the moon? Neil Armstrong. Well done. 10 out of 10. Okay? Right? And one of the first science experiments they did is they took a pendulum and they set it up and they knew the length of the pendulum and they measured the gravitational and they measured the period of the pendulum. They used that to calculate the gravitational acceleration on the moon because they didn't know what it was on the moon because they hadn't landed on the moon before. So that was one of the key things that they did. So they literally took a pendulum, set it up, took a stopwatch, measured it, and that's how we figured out, that's how we determined the value of little g on the moon. Okay, so there's our historical perspective. On number 9, and again, I promise you, there's going to be a problem like either 9 or 10 on the test tomorrow. It's going to be in the middle of the back page. Okay, I'll even tell you exactly where it's going to be. It's in the middle of the back page. Questions 9 and 10. Okay? So, let's talk about number 9, make sure everybody's cool with this. So on number 9, here's the sun, here's the earth. We're going around like this. Okay? So, all you're doing is trying to find the velocity. All you're doing is taking distance and dividing it by time. That's all you're doing. But how are you going to calculate the distance that the Earth travels? What are you going to find?
Circumference.
The circumference of the circle. Oh, okay. Well, that's 2 pi r. That's cool. Now, why do we use uppercase T?
It's the period.
Because that's when it's going to come, that's how long it's going to take for it to come back. So when you celebrate your birthday, you are completing an orbit around a star. Okay? It's like, from an astronomical standpoint, it's like, okay, hey, I completed another loop, you know, another lap around our star. Okay, cool. All right. And so because Earth, we're in the Goldilocks zone, not too close, not too far away from the star that we're on. What do we use for T? 365 days, right? But if you take now, in what units did I give you the radius?
Kilometers.
Kilometers. Oh, I just gave you that in kilometers. So what are you going to have to do with the days? Change them into hours. So then you're going to take kilometers up on top, divide that by hours. So you're going to take 2 pi times, what is it? Was it 1.50?
Times 10 to the 8.
Disturbing that, you know that. Kilometers, and then you're going to do, oh, that's not what I want. See if we want that. Right now I have a random square. Okay, 365 days, 1 day, 24 hours. Now, here's where you have to be careful when you punch this into your calculator. Your calculator will completely roll you under the bus if you do this wrong. What some people do is they'll go out and they'll find this answer separately. And then they'll go through and they'll find this answer separately and they'll write them both down. You don't have to do that. It's a god-awful amount of work, but if you like to, that's fine. But if you can do that, when you do like a sub-calculation, if you're going to do this and get a separate number, keep a lot of digits in that answer. Okay, in other words, don't round that one. You want to round when you get to the end. Or your calculators will handle all of this at once, but here's what you have to be very careful of. You can multiply all that together, but if you just put divided by 365 times 24 and not put that in brackets, what your calculator will do is will take this number, it will divide it by 365, get an answer, and then in its mind it will multiply that by 24. Instead of dividing it by the product of 365 times 24. Okay? So you have to be very careful about how you punch that into your calculator. Calculators are a wonderful thing. They're cool. It makes life a lot simpler. But you have to be very careful about how you punch those numbers in. Next conversion, you want to do the kilometers per hour into meters per second. So this answer should be like 1-ish times 10 to the 5th. Okay? So what you should get out of this answer for the velocity of the Earth as it orbits around our star is going to be about 1 times 10 to the 5th kilometers per hour. Okay? Promise you, you've got to do this conversion tomorrow. So 1 kilometer is 1,000 meters, okay? 1,000 meters, and then 1 hour is 3,600 seconds. So here's the short version. You can take this answer in kilometers per hour, about 1 times 10 to the 5th. Here's 1,000, here's 3,600. You can actually like mark out zeros, and the shortcut is that you multiply by 10 and you divide by 36. Okay? That's the short version. So anytime you convert kilometers per hour into meters per second, and you're going to do this on the test tomorrow, you mark my words. The short version is, it's simple to remember. You multiply by 10, and then you divide by 36. That's it. Now, so your answer to that number 9 in kilometers per hour should be something times 10 to the 5th. In meters per second should be something times 10 to the 4th. Okay? Now, let's talk about number 10. Number 10 creates a problem. Because I'll tell you right now, if you do 10 right, and what we're talking about is here's Big Al, right? And he's at the equator and he's moving around in a circle. Your answer to 10 in meters per second should be around 460. Okay, so if you do that right, you should get around 460 meters per second. This is why this created a huge problem. We've known the radius of the Earth since antiquity. It's a cool deal. It has to do with like a hand-dug well and a tower some distance away. It's a long story. But we've known the radius of the Earth and the circumference for quite a while. So then they started doing the math. They said, okay, hey, if the Earth is spinning, how fast are we moving? Well, if you do this right, you're at about 460 meters per second. That's at the equator. We're up here a ways, okay? We're not moving at 460 right now. We're moving at about 400 meters per second. So right now, y'all are traveling at 400 meters per second. The speed of sound is like 330. So right now, we are all traveling faster than the speed of sound. Okay, so if you're applying to colleges, what's your superhuman strength? I could travel faster than the speed of sound. Sounds cool, but everybody else is doing it too. But if that's making you feel good, go with it. So one of the debates was, how do we have oceans? Because I'm guessing at some point in your misspent youth, when you would actually go outside and experience the world and like ride a bike, okay? And you might have, being the rebel child that you were, actually ridden your bicycle through a puddle of water, okay? Right? Yeah. And what happened with that water? Did it stay on the tire or did it go flying off? Flying off. Oh, right. Oh, I'm cool, creating the rooster tail. Woo! Okay. Right? Anyway, so, and that was going at about 20 meters per second. Okay? Well, now the Earth is spinning at about 460 meters per second. So the argument was that if water goes flying off of a wheel at 20 meters per second, and the equator is moving at 460 meters per second, how can we have an oceans? How come all of this water hasn't just like spun off the Earth, and we're just this barren, rocky moon of the sun? Well, what do we have that the tire does? What does the Earth have that the tire doesn't?
Mass.
No, beyond that. It does, but that's what we'll get. Atmosphere is the next discussion. We'll get to the atmosphere in a second.
Gravity.
We got gravity, right? Okay, the tire does too. There's a little bit of gravitational attraction between the water and the tire. Not very much, okay? But we're on this big rock. The rock has a tremendous gravitational field. And later on we'll do the calculations to prove that we have more than enough gravitational force to hold this body of water on here. Or otherwise it would go flying off. Now, here's an interesting idea though. We have this atmosphere, which is a cool deal, right? Lots of oxygen and nitrogen. Without it, we're kind of screwed, right? So, yeah, it says, oh, we don't need an atmosphere. If anybody tells you that, oh, they're an idiot, okay? But it's a very thin layer, okay? It's a very thin layer of atmosphere. We talked about that. You know, you slice an apple in half, the red peel around the outside on a scale, that's our atmosphere relative to space. So that's the only thing that's keeping us from the vacuum of space and allowing us to have weather and any number of things. So it's a pretty fragile world that we live in if you look at it on that scale. So here's the question. The Earth spins counterclockwise, which is why the sun rises in the east and sets in the west. Okay? So as we're spinning, there's two ideas that you can have about the atmosphere, and let's talk about them both. One option is that the atmosphere, which is just a collection of oxygen and nitrogen molecules that you all breathe in and breathe out and have since the day that you came into this world, right, without giving it a second thought. So you've got this atmosphere, there's just this random particles moving around. So one idea is that the atmosphere is actually stationary because it's not, there's nothing to it, it's just molecules of air, you know, oxygen and nitrogen bouncing around. So it actually isn't moving and it's stationary. And the Earth is spinning within it. Okay, that's option number one. Option number two, the atmosphere is actually moving with us as we're spinning around. So one of two things is happening. Either the atmosphere is stationary and we're moving through it, or the atmosphere is moving with us as we go. Which way do you think it is?
Atmosphere moves.
The latter.
I think
I'm gonna
it
go
moves
with
it.
Why?
Because then we'd have 460
Because if you
kilometers
spin an apple,
or meters per second
the
winds.
skin
field
is going
moves too.
around with that.
Oh, if you spin an apple, it's going around with the apple.
That's right.
But that's like a hard lock surface though.
Okay.
That would be like saying I spin an apple.
Hey, Maze Eagles.
No.
Dirt Central has slushies available for $1. Go check them out.
Can we all go down to the school store?
No,
Please.
no.
Make them feel good.
You know why I don't teach freshmen?
Why?
They would ask questions just like that.
But seriously, I was sarcastic.
They'd be serious.
No, he was serious.
I wasn't.
Yes, you were. Don't lie, McGriddle. Okay.
I'll bring
So-
one back. I'll bring one back.
Huh?
I'll bring you one back.
What flavor?
What do they have?
I don't know. Okay, no. I'm kidding. Okay. So, okay, so let's look at it this way. Again, go back to your misspent use, okay? And you're riding around in the back of the SUV or minivan, which all of you did throughout your lives, I'm guessing. And this is back before you became completely engrossed in your cell phone. The only thing you stare at is your cell phone, okay? This is back when you still had a sense of wonderment around of the world around you, and you would actually look outside, okay? Wow, there's a tree. Wow, okay. And now y'all, okay? So, and not only did you used to like, you know, look at the world around you, which you don't do anymore, but you actually would roll down the window and be cool and stick your hand out the window. Do that, okay? Livia, all over it, yeah? Okay, right? And you felt cool, right? Okay, right? I don't even think windows roll down on cars anymore. I honestly don't. Anyway, they do?
Yeah, they do.
Okay, all right. So anyway, so you stuck your hand out, right? And that's about 20 meters per second, let's say, right? And you could like feel the wind moving and it's cool, right? And you put your hand up and it was like, right, kind of go back. Okay? Everybody do that? If you have not done that, you miss out on an aspect of youth that you really need to do. Don't do it necessarily today while you're driving with both hands, but just saying. If you've never done that, do it. So, it's a rite of passage. But,
It's a right passage.
it is. Well, everybody needs to do that. You just feel cool. All right, so that's about 20 meters per second. So imagine if the Earth was spinning through an atmosphere that was stationary, and we're moving at 460 meters per second through a stationary atmosphere. As soon as you stepped outside, what's going to happen?
You're gonna fly into
You're going to break the sound barrier, which is cool, okay? And you are instantly going to get knocked down flat. Okay? So imagine trees. Okay? Trees would be like, okay? Birds, not going to happen. Okay? You know, Stanley the Sparrow tries to fly, bam. Okay? So, what?
Just imagine it in my head.
Okay? And we wouldn't be here having this discussion, right? Because of the fact that we wouldn't have trees or grass, everything would just be, okay? It's a highly technical term. Yeah. Okay. The other thing, in Kansas, generally which direction do storms move? East to west or west to east?
West East.
West east. Now, if storms were stationary, what? Did you guess wrong?
Mary did.
She said it really loud and proud.
Mary said wrong answer very loudly.
Really? I didn't hear it, so if I didn't hear it, it didn't happen.
It's been a long day.
I understand, trust me. I
Can
know
we go back
nothing.
over the footage
Okay.
and see if we hear it?
Because if storms were if our atmosphere was stationary, storms would always move east to west. Because the storms wouldn't move because we would be spinning out from underneath them. Okay? So that was one of the big debates. Like, okay, great. If the atmosphere is moving, what?
There's only 1 minute of battery left on the camera.
Seriously?
Yeah.
See you later.
Okay, stop that for a second. So everybody cool with this one? I promise you on the test tomorrow, you're going to have a question like that. I'm going to give you that equation. On the test, I will give you this. You just have to know how to use it. Okay?
Wait, did you give us the answers, the closest range?
Yeah, on number 10, in kilometers per hour, it should be like something times 10 to the third. And the second answer is about 460.
Oh, yeah.
Yeah.
I gotcha.
Yes?
Now, does the 2 factor in all significant digits, or is it just irrelevant when doing multiplication? Yeah,
Oh, no. Your significant digit calculations only come in with measured values.
cool.
Like the radius or the period, something like that. 2 pi is just, that's a known value.
Okay.
I was looking for this.
Are we good?
That's good.
Now, let's talk about number 11. I promise you, there's going to be one like number 11 on the test. It will be at the bottom of the front page. I'll even tell you what it's going to be. You're going to have a data table like this. You're going to have force and acceleration. What are you going to graph where?
Acceleration.
Force on the
Y-axis.
Force on the y. Is it going to start at 0, 0? Yes. Why?
No.
Nothing's happening.
No force, no acceleration, because Mother Nature is lazy, right? She's not gonna make something accelerate unless you force it to, right? It's not gonna happen. Do you think you're gonna have to find the slope of the line?
Yes.
Do you think
Probably.
you're gonna have to show your work?
Probably.
Yes? Is your slope gonna have the correct units?
Yes.
Am I gonna be happy if you expressed your slope as a fraction?
No.
No.
No. No. And here's the reason why. Fractions don't reflect significant digits. And that's the reason we don't use fractions in...
I am deeply disturbed
Why?
because he was just leaning on me.
You just lay down your head somewhere. Like,
I was going to get his pencil.
Eric needs love.
I do.
We all do. But this is not the time and place. Quit!
You guys doing it now?
We just have to have, we need to have like a man moment, like a group hug or something.
Just that 1%.
No! No. Okay. That's so borderline biology. Okay. Okay. So. It's a little punchy. So, you're going to have your slope, right? It's going to be a decimal. What units is the slope going to be in?
Oh, I know this.
Oh,
Wait, on this one?
yes.
Inverse.
Well, look. This acceleration is going to be in?
Kilograms.
No!
Newtons over, meters over.
Wait, is it?
It's 1 over K.
Yes, it's like
It's the inverse of math.
Okay, stop. Whoa.
Oh, Mr. Burkamp.
Whoa, what?
Isn't Newton's also, you said it was also kilograms and meters per second
It
squared?
is, but that isn't what I asked. I just started with the acceleration part.
Oh, okay.
Okay, you're on step 3, I'm on step 1.
Okay,
Okay, we'll get there, great.
alright.
Okay. So I got an acceleration meters per second squared. The force can be expressed in
Kilograms meters per second squared.
kilograms meters per second squared. Okay, that's kind of cool. These are going to cancel out. You're left with
The inverse of
1 over
mass.
kilograms. So the slope represents the inverse of
Mass.
mass. There, we're cooking with fire. Okay, so you're going to do something like this. You're going to write, and I'm going to ask you to write the general expression for the equation. It's a linear function. You're going to have y equals mx plus b. Is there a y-intercept? No. So you're going to have, what's graphed on the y-axis? Oh, that's acceleration. Then you're going to have the slope multiplied by force. The only thing you're going to have to plug in is the value of your slope. Yes?
Do you want us to graph this on graph paper?
Yes? Yeah, just like a half sheet. Okay. All right. Then either I'm going to give you an acceleration and ask you to find the force, or I'm going to give you a force and ask you to find the acceleration once you have that value. And here's how you can check that you got it right. Go back to your graph, find either the acceleration or the force, and see if your answer kind of matches up. If it does, hey, odds are you did it right. If yours isn't like a coordinate pair, you've done something wrong. Okay? That's the easiest way to check that you see if your answer is right. Okay. Now let's talk about number 12. Okay? There's a beam of light going around the Earth. Kind of a cool problem. So what's happening here is that here's our strange rock. We're going to make this beam of light travel around. So basically, this is just a really fancy way of saying, oh, velocity is distance divided by time. Okay? That's all it is. All this looks horribly complicated. All this is distance divided by time. That's it. Did I give you the velocity? Yes, speed of light, right? Now, what units is that in?
Meters per second.
Meters per second. Now, did I give you directly the distance around the Earth?
Yes.
No, I didn't.
No.
I gave you the radius of the Earth, but do you have the intellectual capacity and calculating ability to find the circumference of the Earth?
Yes.
Yes, but I was a jerk. Why was I a jerk?
Didn't include, well, no, never mind. I mean, never mind. Can't really measure.
Oh, yes, you can.
You gave us this
Formula's
problem.
not there.
Beyond that, that's my job.
Formula is not directly
Wait,
in the
I don't
problem, but it's literally
What
4
units
questions
is the
above.
velocity in? Meters per second. What unit? Olivia, what units is the radius in? Kilometers. So I gave you one in kilometers, I gave the other one in meters per second. Are they compatible?
No.
No, but can you make them compatible?
Yes.
Yes. So this becomes 2 pi over t, right? Okay? So you have the velocity, you have the radius, you're going to solve for a period, how long it takes. Your answer should be less than a second. Okay? Your answer should be less than a second. But here's what's important. Technically, that answer is seconds per revolution. You're figuring out how long it takes to make one revolution. That's your answer to 12A. Now, on B, I want to know how many revolutions per second it makes. So on your equation sheet, I've given you this. Period is the inverse of frequency, or frequency is the inverse of period, okay? Period is how long it takes per revolution. Frequency is how many events happen per unit of time. This is why they're inverses of each other. So to get your answer to 12B, and you're trying to find frequency, how many times per second it's going to go around. So to get frequency, you just take the inverse of period. This is where the miracle happens. Really not a miracle, but here's the deal. Your answer to 12A is in seconds per revolution, right? What do you want the answer to be in? Revolutions per second. Oh, look, the revolutions flip up, you get revolutions per second. That's cool. So your answer to 12B should be around 7. Okay? Should be around 7. So here's the cool part of this, if you think about it. And I gave you this problem just so you can kind of understand just how fast the speed of light is. So you're here, turn that thing on, you're going to see this beam of light go all the way around you 7 times per second. Now, McGriddle claims that he can count to 7 in less than a second. We'll see. But here's the point. You're going all the way around the Earth 7 times in a second. That's fast. Okay? It's cool. All right. Make sure on number 13 that you've actually told me what happened. Don't just say, oh, it's different. Oh, it changes. Oh, it increases. Oh, it decreases. Since I specifically said what's happening to the period or what's happening to mass, whatever it is, you need to specifically state on 13 how that is changing. Yes?
So on 12, the label for B would be revolutions per second?
Yes. Hunter?
What's the physics behind why we can't feel that we go 7 times around in 1 second?
We don't. I'm saying if it was a beam of light.
Why no? But why can't? Oh, we don't.
We don't. No. Oh, God, no. Oh, no.
I was gonna say, why can't we feel that? Never mind.
No. Well, in a similar type vein, that was one of the questions. Why don't we feel like we're moving at faster than the speed of sound right now? The analogy is, it's like you're in a plane. Okay, you're in a plane cruising at 30,000 feet. You don't get the experience that you're traveling at 500 miles per hour, because everything is moving at 500 miles per hour. It's like, you sound like a nerd, but you can bet someone's like, hey, I can run at 502 miles per hour. It's like, no, you can't. It's like, sure. You're in a plane, right? The plane's traveling at 500 miles an hour, and then you just walk forward in the plane, and it's an additive property. It's like, oh, yeah, I'm traveling at 502 miles per hour. Boom, there you go. You like that?
I'll have to use that one.
Okay, yeah, it's like, hey, I can travel 500. Yeah. Okay. Now, anything else you want me to go over? At all? If I'll be here at 6:30 tomorrow morning. If you have this done and you want me to look over it, I will. Okay. If you want to come in during encore and ask me to look over it, I will. Okay. But it is due tomorrow with the test. Okay. Good. Once, twice, so we can stop that. So test tomorrow, it'll be the shortest test that you will have in this class. It'll be 1 page, front to back. Okay? The beginning, probably 7, 8 questions, are going to be multiple choice. So this is what I'm going to ask you, like, for example, here's a lab situation. Like, that's when I'm going to ask you kind of the definition terms, like what's the difference between precision and accuracy. So what do you have to talk about accuracy?
An accepted value.
An accepted value. It's like the Siri test. If I say, hey, if I can ask Siri, like, Siri, what is the mass of the moon? Okay? And Siri's probably going to go out and find me an answer. So that if I do a lab and I can compare my measured value of the mass of the moon to something that Siri is going to tell me, I can talk about the accuracy because there's an accepted value that I can compare it to. Okay? Now if I say, hey Siri, what's the accepted time for a penny to fall in Burkamp's room as measured by a pencil sliding down a coiled spring? Okay? Again, Siri is sending you to, like polka sounds or music or something like that. Siri is going to flip out at this point. So, because there is no accepted value. So, you can only talk about accuracy if you have something to compare it to. We can compare our data of the mass of the moon to an accepted value. That's kind of the litmus test. Now, with precision, there's two parts to precision. Obviously, it's the number of, as First Block put it, the number of itty-bitty marks on the measuring device. The more itty-bitty marks you have, the more precise it is. No, I'm not going to put that as a multiple choice answer, itty-bitty marks. But you get the idea. The other way to look at precision is that do your measured values, are they relatively close to each other? So if you're dropping a pencil down a spring and measuring how far it travels, how much variation is there in your data? If your data is all very close together, you have precise set of measurements. If your data is all over the place, then you're not precise. Okay, so there's two aspects of precision. The actual measurement itself, and then a comparison of your data to see how close they are to everybody else. Okay? Independent, dependent variable. Where are you going to graph the independent variable?
On the x-axis.
The x-axis. Dependent on the y-axis, right? Make sure that you understand the difference between the two of them. Remember, where is time always going to go? X-axis or y-axis? X. Okay, because it's always position is a function of time. Velocity is a function of time. Acceleration is a function of time. Okay? Cool with that. All right, got that one. Dimensional analysis, I promise you, you're going to have to do probably 2-dimensional analysis problems. So here's what I might do. I might give you something like this. F equals mass times V minus V naught over distance. Okay? So I might give you something like that and say, okay, hey, is this a valid equation? All right? So here's where this is going to go south from the beginning. When you see that M, are you going to substitute in meters, or are you going to substitute in kilograms?
Kilograms.
Kilograms. Why?
Mass.
That's mass. If I wanted meters, what would I put? Distance, X, L, something like that. So when you see M, listen to me. That is not meters. It is mass, and it's put in as kilograms. Okay? So, remember, listen to me. Dimensional analysis is a process. It is not about writing down the units and then a miracle happens and, oh, the equation is valid. Okay? No. Now, if there was a 2 in front of there, let's just say, if there was a 2. If you're doing dimensional analysis, would you worry about that 2?
No.
No. Why not?
Because it doesn't matter.
It doesn't change the units. Okay? So if there's a fraction, whole number, something like that, don't worry about it. It's not a factor in the dimensional analysis process. Now, the other thing I'm going to make you do is some simple algebra. I'm going to give you an equation, and I'm going to say, hey, solve for this equation. If all I tell you to do is solve for the equation, do not do dimensional analysis. Now, if you want to see if it works, hey, that's cool. That's your game if you want to. But if I want you to do dimensional analysis, I will tell you, do dimensional analysis. Okay? I promise you, you're going to have to be able to work with this equation, 2 pi r over t. Okay? It's going to be Mars. I'm going to tell you right now, it's going to be about the planet Mars. It's going to be on the back side about halfway down the test. That's where this problem is going to be. and you're gonna have to do two answers. One in kilometers per hour and one in meters per second. So you have to be able to do that conversion cold, kilometers per hour, meters per second. I'm going to give you one problem where I'm going to ask you to multiply or divide two numbers together and write your answer with the correct number of significant digits. I'm going to give you one problem where I'm going to ask you to add or subtract and make you write the answer with the correct number of, with the correct precision. Okay? That's going to happen. You're going to have a force and acceleration graph that you're going to have to draw, label the axes, find the slope, show your work. You all know the drill at this point. Okay? That's about it, right? That's the test. So multiple choice, the force and acceleration graph, dimensional analysis, solve an equation, problem using this, then another dimensional analysis problem, okay? That'll be the test, simple as that. So, any questions from your side before we move on about the test, what it's going to be like? Okay. Now, here's the other thing that's going to happen on test day, just so you all know ahead of time. On test days, one person per table is allowed to sit, okay? Which means I'm going to have, like, you can, one of you is going to have to move, either like the back of the room, table, somewhere. There's always two versions of the test, okay? Like an A version and a B version. Not that any of you would cheat, but I just want to make sure that you don't know what anyone thinks about it. I'm also going to give you a laminated version of your big art equation sheet so that you have that for the test. You will always have that. You don't get your own. You have to use mine. And then you do the test. If you want to bring a ruler to draw the graph, recommended, not mandatory, but you might do that because eventually you got to have a ruler and protractor for this class anyway, so just go ahead and get it. And then when we get done, we'll start talking about velocity, and you won't have any homework over the weekend. So that's the drill. Good? Fantastic? Okay. So here's the next part. So I've got first blocks labs, and they're going to do, you're going to do their labs like they did your labs, which was interesting to see. Okay? And yeah, it was interesting. Let's just put it that way. So I've got 6 of them, and there were six groups of their labs. There were 6 of you. So what's going to happen is that you're going to go back and grab a lab. Try not to do one that was kind of similar to what you did. One of you is going to have is going to require a balloon, and let me know and I'll get you the balloon. So you're going to rate them on 2 different things. Primarily, you're going to rate them on the procedure. So you're going to read the procedure and you're going to build what you were told to build. Okay? Now, if they just say, take a block and set it on the table, you get to pick where, unless they specify where to put it. So you're going to try and build what they built. You're going to rank them on a scale of 1 to 5. 5 being, wow, this was spot on easy, you guys are magnificent. 1 being, you couldn't teach a fish how to swim. Okay? So, somewhere in between. Now, if you want to make a constructive comment, okay, constructive, like, we had no idea what you meant on step 3. Okay? That's cool. You cannot assign anything in between. These are whole numbers. You cannot give them like a 3.33. It's 1, 2, 3, 4, 5. Then, listen to me. I want you to run the 5-penny trial 5 times. Don't do the single penny, don't do the 10. That was kind of a nice medium thing. And then you're going to compare your data to their data. Now, if their average is like 33 centimeters and you get an average of like 34 centimeters, hey, that's cool, right? Now, if they have an average of 33 and you have an average of like 5, okay, that's bad, right? Because that's the mark of any good experiment, is the ability for your data to be replicated. Because if your data can't be replicated, nobody's going to believe what you did, okay? So, when you get done, you're going to build it, rank them on both, and then staple this to the back of the lab and give it to me. Okay? Staple this to the back, give it to me. I'm done, so you got the rest of the time to do this. If you get done, you want to work on that review, you can, but that's it. Let's go.